Hello everyone, welcome to day 3 of our deep dive into BERTopic. Today, we'll explore the inner workings of BERTopic, focusing on how it utilizes BERT and other advanced techniques to model topics effectively. BERT, the short form of bidirectional encoder representations from transformers, is a powerful deep learning model known for its contextual understanding. This capability allows BERT to differentiate the meaning of words based on their context, which is a significant advantage over traditional models that assign a fixed meaning to each word. For instance, in the sentences, "I went to the bank to deposit money," and "I sat on the river bank," BERT can distinguish that bank refers to a financial institution in the first sentence and the side of a river in the second. Today, we will also delve into the code behind these concepts to see how they work in practice. Here's how you can see this in action with some code. In this example code, first we are loading the pre-trained BERT model and tokenizer from the transformers library. Second, we tokenize the two sentences and convert them into input IDs. Third, we pass this input IDs through BERT to get the embeddings for each word in the sentences. Fourth, we use torch.no_grad function. It is a context manager provided by PyTorch that disables gradient calculation. Because when you are performing inference with a neural network, such as using BERT to get embeddings, you only need to do a forward pass through the network to get predictions. You don't need to calculate gradients, which are used during training to update the model's weights. Disabling gradient calculations saves memory and computational resources, making the process more efficient. Then we pass the tokenized inputs to the BERT model. This input syntax unpacks the dictionary of inputs, which includes items like input IDs and attention masks, and passes them as arguments to the model. The model processes the inputs and produces an output, which typically includes the embeddings for each token in the input sentences. This part of code efficiently obtains the embeddings from BERT while ensuring that unnecessary computations, like gradient calculations, are not performed during inference. Fifth, we use cosine similarity to compare these embeddings and print the output. The cosine similarity score will indicate how similar the meanings of bank are in the two contexts. A lower similarity score shows that BERT understands the different meanings based on context. In the output, the warnings indicate parameter renaming issues within the underlying libraries. These warnings are non-blocking and do not affect the execution of your code. They are simply informative messages. To suppress these specific warnings and keep your output clean, you can use the warnings module as shown in your code. The cosine similarity score is 0.43. This value ranges from -1 to 1, where 1 indicates that the vectors are identical. 0 indicates that the vectors are orthogonal or having no similarity. -1 indicates that the vectors are diametrically opposed, in other words, completely different from each other. A similarity score of 0.43 indicates that BERT recognizes that the word bank, in the two contexts, financial institution and river bank, has different meanings but with some contextual similarity. This example demonstrates how BERT uses context to differentiate the meanings of the same word in different sentences. Next is embeddings. The BERT converts words into vectors, which are numerical representations capturing the context and meaning of the words. This allows BERT to understand the nuances and relationships between words in a given sentence. Here's a simple example to illustrate how BERT generates embeddings for words. Again, first we are loading the BERT model and tokenizer from the transformers library. Next the sentence is tokenized, and the tokens are converted to input IDs suitable for the BERT model. Then we get the embeddings. Using torch.no_grad function, we perform a forward pass through the BERT model to get the embeddings without calculating gradients. And extracting embeddings and for all tokens in the sentence embeddings are obtained from outputs. Last_hidden_state. For analyzing embeddings, we print and the shape of the embeddings tensor is printed, which will show the number of tokens and the size of each embedding vector, typically 768 for BERT base. The specific embedding for the word bank is extracted and printed, showing its numerical representation. The output from the code consists of two parts: the shape of the embeddings tensor and the actual embedding vector for the word bank. The tensor shape, torch, size 1, 13, and 768, indicates that the batch size is 1 since we have only one input sentence. 13 is the number of tokens in the tokenized sentence. And 768 is the size of the embedding vector for each token, standard for BERT base. When BERT generates embeddings, it converts each word into a 768-dimensional vector. Each of these 768 dimensions captures different aspects of the word's meaning and context. Think of it like a detailed fingerprint for each word that includes nuances and subtleties in its usage. Let us now understand the clustering with BERTopic. So, after the BERT has created these embeddings, BERTopic clusters them, means grouping similar texts together. Here's how it works. BERTopic uses a clustering algorithm called HDBSCAN, short form of hierarchical density-based spatial clustering of applications with noise. This sounds complex, but it's quite handy. It handles noise. It can deal with noisy data like irrelevant or random data points. And it can find clusters of different sizes and densities. Let's see how you can use HDBSCAN with some sample data. In this example again, first we import the libraries, such as HDBSCAN for the clustering algorithm, NumPy for handling data, Matplotlib for plotting the results. We create sample data of set of 2D points to demonstrate clustering. Then we are creating HDBSCAN model, using HDBSCAN.HDBSCAN_win, with min cluster size equals 2, it initializes the model, with min cluster size set to 2 as the minimum size of clusters. Next, we are fitting the model, cluster labels equals clusterer.fit_predictive data. This syntax fits the model to the data and predicts cluster labels. Then we are using Matplotlib to plot the data points, colored by their cluster labels. The output plot shows the results of clustering using HDBSCAN. The data points are grouped into clusters, represented by different colors. In the plot there are 3 distinct clusters: purple, green, and red. We know that HDBSCAN can handle noisy data, but in this specific example, it seems that all points have been assigned to clusters, with no apparent noise. And also, as HDBSCAN can detect clusters of varying densities. In this example, the clusters have different numbers of points, which HDBSCAN can handle effectively. HDBSCAN effectively identifies and clusters data points into groups of varying densities, making it useful for real-world applications where data may not be uniformly distributed. For example, imagine you have a bunch of product reviews. HDBSCAN can group reviews mentioning battery life into one cluster, design into other, and performance into another. This way, you get clear topics from a large set of texts. To demonstrate grouping with a set of synthetic reviews that cover different aspects of product features such as battery life, design, performance, and other features is shown in the code here. The reviews are converted to numerical vectors using TF-IDF, capturing the importance of each word in the context of the reviews using vectorization. Next, HDBSCAN is used to group the reviews into clusters based on their content. Reviews mentioning similar aspects are grouped together. And for visualization, we are using PCA to reduce the dimensionality of the vectors to 2D for plotting. And then, we plot the 2D representation of the reviews, colored by their cluster labels. In the scatter plot, each point in the scatter plot represents a product review. The points are colored based on the cluster labels assigned by HDBSCAN. The different colors represent different clusters. And for the clusters, the plot shows several distinct clusters, where points of the same color are grouped together. For example, the red points at the top right are grouped together, indicating they share similar content. And for the noise, if there were any points colored differently from the clusters, they would be considered noise by HDBSCAN, not assigned to any cluster. To summarize, BERT understands the context of words and creates detailed, context-aware word embeddings. And the HDBSCAN groups these embeddings into meaningful clusters, handling noise and varying densities. By combining BERT's deep understanding of language with the HDBSCAN's powerful clustering, BERTopic can efficiently and effectively identify topics within a large set of texts. Let's now dive into hierarchical clustering and how BERTopic uses it. The hierarchical clustering is a clustering method that builds a hierarchy of clusters, creating a tree-like structure of topics and subtopics. It allows you to explore data at different levels of detail. There are two methods for this, the bottom-up approach and the merging clusters. The bottom-up starts with each data point as an individual cluster. Merges the closest pairs of clusters step by step. And in the merging clusters, as clusters merge, you can see how individual data points form larger clusters. The dendrogram visually represents this process. So, in the both examples below, starting with the agglomerative approach, the dendrogram, representation of hierarchical clustering, where each leaf represents an individual data point. The branches shows how clusters are merged. And the height represents the distance at which clusters are merged. In this case, the dendrogram starts with each data point as its own cluster and merges them step by step based on their similarity. And for the merging cluster, similar to the first example, this dendrogram shows hierarchical clustering but using the complete linkage method. The leaves represent individual data points. The branches indicate how clusters are merged at each step. And the height, distance between clusters when they merge. Let us now understand the difference between the bottom-up approach versus merging clusters in hierarchical clustering. From the concept perspective, the bottom-up approach, also called as agglomerative clustering, think of it like starting with each person at a party standing alone and then gradually forming groups based on who they talk to. While the merging clusters is about showing how these groups come together step by step until everyone is in one big group. In the bottom-up, everyone starts alone, while the merging shows the process of groups forming over time. The bottom-up focuses on the beginning when each person is alone, while the merging focuses on how groups combine over time. The bottom-up groups merge based on similarities until everyone is in one big group, while merging visualizes each step of groups coming together. Both use a dendrogram, a tree-like diagram, to show how clusters form and merge. The bottom-up emphasizes the initial phase with individual data points, while the merging emphasizes the intermediate and final phases where clusters combine. And in the bottom-up, the hierarchy formation starts from the bottom with individual data points and builds up, while the merging shows the hierarchical levels of merging from small clusters to larger ones. Let us now understand why hierarchical clustering is useful. So, the hierarchical clustering allows you to start with broad topics. For instance, you might group articles into categories like technology and health. You can zoom in to see more specific subtopics within these broad categories. For example, within technology, you might find subtopics like artificial intelligence, blockchain, and cybersecurity. This multi-level exploration helps you understand data from both broad and detailed perspectives. It's especially useful for datasets with different levels of detail. You can adjust the level of granularity based on your needs. For example, in a customer review dataset, you might start with general topics like product quality and customer service, and then dive deeper into subtopics like battery life, design, and performance. By examining both the high-level and detailed patterns, you get a comprehensive understanding of the data. This helps in identifying overarching trends as well as specific issues or areas of interest. For example, you might find that battery life is a common issue in many product reviews, while design has mixed feedback depending on the product model. In summary, the hierarchical clustering is a powerful tool that adapts to the complexity of your data, providing insights at multiple levels of granularity and flexibility to cater to various analytical needs. Okay, let us now discuss about the role of UMAP in BERTopic. The UMAP short form of Uniform Manifold Approximation and Projection is a technique that reduces the number of dimensions in your data. Here's why this is important for BERTopic. The BERT embeddings are often very high-dimensional, meaning each word or sentence can be represented in a space with many dimensions such as 768 dimensions for each word. For example, imagine you have a spreadsheet with 768 columns. Each column represents a different aspect of a word's meaning. Working with such high-dimensional data is complex and computationally expensive. The UMAP helps by transforming this high-dimensional data into a lower-dimensional space, typically 2 or 3 dimensions. This makes it much easier to visualize and understand the data. Think of it as turning a 3D object into a 2D drawing. It's simpler to see the overall shape. Even though UMAP reduces the number of dimensions, it tries to keep the important relationships between data points intact. For example, if 2 words are similar in the high-dimensional space, they should still be close to each other in the lower-dimensional space. In BERTopic, UMAP plays a crucial role in making the topic modeling process more efficient and effective. By reducing the dimensions of BERT embeddings, UMAP allows us to visualize clusters of topics in a 2D and 3D space. This visualization helps in understanding the relationships and similarities between different topics. The UMAP preprocessed data is more manageable for clustering algorithms like HDBSCAN. The reduced dimensionality ensures that the clustering algorithm can efficiently identify meaningful clusters without being bogged down by the complexity of high-dimensional data. To understand the practical implications, let's look at an example scenario where UMAP is used in BERTopic. The initial embeddings start with high-dimensional BERT embeddings for a collection of documents. Each document is represented by a vector of 768 dimensions. Next, apply UMAP to reduce these embeddings up to 2 or 3 dimensions. This step simplifies the data while retaining the essential relationships between documents. Next, plot the reduced embeddings on a 2D plane. Clusters of points become visible, representing different topics. This visualization provides an immediate understanding of the data structure. Use the reduced embeddings for clustering with HDBSCAN. The clustering algorithm can now efficiently group similar documents into topics based on the reduced dimensional space. And analyze the resulting clusters to interpret the topics. The reduced dimensions and clustering make it easier to identify and understand the main themes in the document collection. In conclusion, UMAP's role in BERTopic is to streamline the topic modeling process, making it more efficient and insightful. And by reducing dimensionality, UMAP helps in visualizing and clustering data effectively, ultimately leading to better topic discovery and understanding. The benefits for BERTopic ID. The visualization. It is a crucial benefit when using UMAP in BERTopic. By reducing high-dimensional data, like BERT embeddings, to 2 or 3 dimensions, UMAP makes it possible to create visual plots that help to see how topics are distributed. This visualization not only helps in understanding the structure of the data but also in communicating insights to others. For instance, in a scatter plot, you might see distinct clusters representing different topics like battery life, design, and performance in product reviews. This visual representation can be invaluable for presentations and reports. Efficient clustering is another significant benefit of using UMAP in BERTopic. High-dimensional data is complex and computationally intensive to process. When UMAP reduces this data to lower dimensions, clustering algorithms like HDBSCAN can work more effectively. Why is this important? As the lower-dimensional data requires less computational power, which speeds up the clustering process. Moreover, the clustering results tend to be more meaningful because the noise and redundancy in high-dimensional data are minimized. By simplifying the data, UMAP enables HDBSCAN to identify clusters more accurately. This efficiency is particularly important when working with large datasets, as it ensures faster processing times and more reliable topic modeling results. And the reduced complexity also means that the clustering algorithm can focus on the true structure of the data, leading to better defined and more interpretable topics. Understanding these processes not only enhances your grasp of BERTopic but also equips you with the tools to apply these techniques to your datasets effectively. As we move forward, you'll see how these foundational concepts come together to create a powerful topic modeling tool. In today's session, we delved into the intricacies of how BERTopic leverages BERT for contextual understanding and HDBSCAN for effective clustering. We explored how BERT's embeddings capture the context and meaning of words, enabling BERTopic to differentiate between nuances in language. By using HDBSCAN, BERTopic can group similar texts into meaningful clusters, even in the presence of noise and varying densities. Additionally, hierarchical clustering allows for multi-level exploration of topics, providing both high-level and detailed insights. Thank you for joining today's lecture, and I look forward to our next session, where we'll continue to explore the capabilities of BERTopic. We hope you found the content informative and helpful. If you have enjoyed this video, please give it a thumbs up, share it with your friends, and don't forget to subscribe to our channel for more educational videos. Your support helps us create more valuable content for you. See you in the next video. Thank you for watching.